Great. Thank you, Janusz. Thanks for the introductions. Thanks for having me. Yes, I'll be talking about impacts of inverter-based resources such as wind, solar, and storage on power systems today. My presentation is fairly broad and high level. I just wanted to talk about different kinds of impacts and also why it's different today. Why didn't we talk about it before? So just Janusz mentioned, I'm from Energy Systems Integration Group. Just a few words about us. We are not a consultant. I like to think about us as a think tank, although the founder of ESIG, he doesn't like this word because it's like a new buzzword. But basically, we're conducting industry forum to discuss issues related to energy transition. So we do it through a number of workshops throughout the year, but we also conduct a number of working groups where we bring industry members together to discuss questions that they are working on in their shops, but we do it collaboratively. And then we release some kind of publications, reports that then they can use in their work. So that's kind of how we work, and we're also an active member of Global Power System Transformation Consortium, as Janusz mentioned. We have now more than 200 industry members, and as you can see, they're from various industry sectors, developers of renewable resources, forecasters, consulting firms, system operators, and utilities. So what is the goal of today's presentation? As I mentioned, I'll introduce challenges associated with integration of wind solar storage into power systems. I'll try to explain why these challenges are relatively new. I'll provide some indication where there are mathematical modeling and statistics where they can help us. And also we'll use some examples from Texas. As Janusz mentioned, I worked for 10 years in ERCOT, who is a system operator in the state of Texas, and the system is relatively interesting. It is an almost electrical island and also has high shares of renewables. So I was thinking before putting the slide together, I was thinking to provide some background about, how much megawatts is installed in different countries in the world of wind and solar and storage. But I think megawatts is very hard to, put into perspective because different systems are different sizes. They have different amount of interconnection to the rest, of neighboring countries. So I thought this graphic is relatively good because it shows on x-axis, it shows system size. And by system size, it means peak load in gigawatts, and then percentage of wind and solar on y-axis. And here you can see different islands and countries, different power systems listed in each bar. And the circle shows annual energy percentage that is served by wind and solar in a year. And I believe the figure is from 2020. And then the red circle is showing instantaneous penetration of wind and solar as a share of load. So basically, if we take ERCOT as an example, this bar here is showing that ERCOT peak load is around 80 gigawatts right now. About 26% of energy in a year is being served by wind and solar resources, and then instantaneously they actually had a new record, which was 69%. So 69% of load at a given instance in time was served by just wind and solar. And so you can see that some of the systems that are small, islanded systems, they are already close to 100% or 100% instantaneous penetration, and the energy impact from wind and solar is also pretty high. But as you move towards the right and towards larger systems, you can see that these percentages annually are not as high, and also instantaneous penetration is not as high yet. Still, for large systems like Ireland and ERCOT, these numbers are pretty high, and this is unusual because we are not used to operate power systems with such large amounts of wind and solar. And as I'll talk about later in my slides, this technology is very different from what we used to operate before. So this presents a number of challenges that I'll be talking about throughout my presentation.
Julia, sorry to interrupt you. There's no Britain on it. So if I remember correctly from last week's presentation by Cherokee, I think this country we have about, on average, about 30% average, and the maximum about 60% instantaneous. So
yeah, that sounds about right. And also for Ireland, this figure is now from 2020. They now reached 75%. They actually have more wind and solar to have higher penetration, but because of technical issues that, again, technical challenges that I'll be talking about later, they need to constrain it right now. So they keep certain amount of conventional thermal generation, coal-fired, gas-fired generation still online to provide some of the grid services, because currently this grid services cannot be provided by wind and solar that they have installed today. So they keep it at 75%, but theoretically it can go higher with amounts of wind and solar that they have installed.
So Britain, in other words, would be slightly to the left of ERCOT, just for people's information, but very, very similar number. Do you have any nuclear in Texas or not?
Yes, we have 2 power plants, 2 units at each plant, and total installed capacity around 4,000 megawatt. And so that's compared to 80,000 megawatt load. So it's a small portion, but it's still it's still a good chunk of base load. All right. So as you know, there is change happening in generation mix towards wind and solar, and so it leads to a number of challenges. So wind and solar plants are usually built in areas with best wind and solar resource, so good wind speeds, high irradiance, usually open grounds, and land should be available so that these plants take more. They have a bigger footprint than conventional thermal power plants. So usually these places are far away from where electricity demand centers are, and also far away from where currently we have conventional power plants, because conventional power plants, unless they were hydro, they were built closer to loads because just of convenience and to minimize losses. So basically we're having the shift of generation from demand centers where they were close to demand centers before, further out in the grid where there is little load, and they are far away. So that power needs to be transmitted. So power grid normally is not built out to these areas. So it's usually either relatively weak, so there will be just a few links, or there is no power grid at all. And so there is a need for more transmission, and where there is transmission, there is a need for transmission reinforcement to allow connection of this wind and solar resources. Wind and solar resources are variable. So again, that's something we haven't had before. When you have conventional thermal power plant, it's relatively easy to dispatch between, its minimum load level and maximum production level, and you can dispatch it at will. The only uncertainty you have if a generator goes on forced outage, so there is some kind of, something breaks in the plant and it's forced out. Whereas with wind and solar, production varies all the time with availability of wind and solar irradiance. And so it needs to be balanced so that load is always supplied, and it needs better forecasting so that we know what's coming up in the next couple of hours ahead. Wind, solar, and battery storage technologies are different from conventional traditional large generation, and I'll talk about it a little bit later in more details. And so that introduces new technical challenges. Wind, solar, battery storage generation technologies are more complex. They've been developed in the past maybe 20, 30 years. They are less streamlined. So this technology allows a lot of flexibility in controls. And so controls may vary by manufacturer, even though they provide kind of similar functionalities, the way controls are implemented can be different. Whereas with conventional synchronous generators that we had before, over the years that we had them, they are relatively, typical and streamlined and much easier to model. So what we are faced with now is higher complexity with modeling and simulations. So it gets to a point where you need to represent each wind and solar resource by, model that's provided by manufacturer to be able to capture some of this controls. So now I'll go through this. I spoke high level about these challenges. I go a little bit more in detail with each of the challenges. So the first one was, need for transmission. And here I brought up a map of Texas. So what you see in blue is that area that is served by Electric Reliability Council of Texas, which is independent system operator that covers 90+% in the state of Texas, but not the entire state. So that's the blue territory, is the service territory of ERCOT. And so really good wind conditions are there in the west. And in this, let me bring a laser pointer. Yeah, so in this upper part of the state, wind conditions are so good that they are comparable to offshore wind. So the amount of energy that you can capture is comparable to offshore. So really good conditions. Almost nobody lives there, so it's very little load. Originally, ERCOT didn't even have a grid there. So once wind resources started developing there, the new grid had to be built there. And in this part of Texas, in the west part, there is a really good solar conditions. Whereas you can see all big cities in Texas marked up here, and they are either in the central or eastern part. There is really large distance. I think like one corner of the state to up to here, it's about 800 kilometers, if I remember correctly, but don't quote me on that. But it's a really large distance. The problem is that if you start transferring power over very large distance, you start facing problems with voltage stability. So just to kind of visually explain it, as you transfer more and more power, voltage along the transmission line falls. And so there will be a limit of how much power you can transfer. So normally on a transmission line, you'll have a thermal limit. So it has like current carrying capability and maximum current that you can send along the transmission line. But if it's really long distance and you send a lot of power across that line, there may be a voltage stability limit, which is below the thermal rating of the line. So theoretically, you could have sent more power over it, but because it's really long distance, you're not able to utilize the lines to its fullest. And so it requires other solutions to be able to transfer more power. There is something that's called series line compensation. So it's basically you are lowering electrical distance between generation and load by installing the series compensation devices along the transmission line. But there is also a limit of how much you can achieve with that. You can build more parallel lines, so that allows you to transfer more power. Again, by building more parallel lines, it kind of effectively decreases distance between generation and load, electrical distance. Or you can build high voltage DC where voltage stability is not a problem. It's direct current, and you can transfer more power over a longer distance. But this is more expensive and kind of like traditionally, it's not a solution that ERCOT is looking at. They've done a number of planning studies where they considered it, but it's still economics do not pan out for HVDC transmission from within the state, from western part to the east. So storage may help to shift generation from periods with high wind or solar production to periods with low production. So with that, you can utilize existing transmission to its fullest, because say there is no solar production at night, so you can use storage during that time. But on the other hand, for example, in ERCOT, wind at night is the strongest, so there is again a limit of how much you can kind of optimize between these three types of resources and transmission that is available. But coming back to mathematical problem, there is a optimal sizing and placement of storage that is needed. So I show this problem with example of Texas, but globally, this problem also exists because the way transmission system was developed was around load centers and around centrally located generators, and now these resources are shifting to other areas. So there is a need for microgrids, macrogrids, so kind of bigger overlays, maybe higher voltage, maybe HVDC. You might have heard about offshore grids. So there are these ideas of interconnecting offshore wind farms with a grid and then connecting it to shore in different countries. And basically having a meshed grid also provides more reliability, and you can allow alternative passes for power transfer. HVDC overlays I mentioned, so that allows longer distance transfer with less technical challenges compared to alternating current. Longer term storage is something that is really needed right now because of variability and uncertainty of wind and solar resources. I don't think there is commercially available and economically feasible long-term storage yet, except for pump hydro or hydro storage. But that's something that industry is working on, and it's really needed as we start getting into higher shares of wind and solar resources. And then we need the ability to model and simulate really large complex systems with many constraints and many potential options to test. So we need to start looking at different scenarios, longer time scales, bigger systems being interconnected. We need to model all these transmission constraints. And so that introduces a computational challenge. So now I switch gears to talk about variability. There can be severe changes in wind generation output that is caused by different types of weather events. And this can cause large ramps. What I have here on the right-hand side is what's called power curve. So this is, you can think of it as one wind power plant. But there is a curve like this for every turbine in this plant. It's just like cumulative. If you see, it combines to 100 megawatts. So it tells me it's for the entire plant, not just one turbine. And so on x-axis, you can see wind speed in meters per second, and on y-axis is power produced in megawatts. And you can see that power that wind power plant can produce varies with wind speed. And this variability is the highest in the range between 4 and 12, or maybe 15 meters per second. It differs depending on technology. But basically, if you are in this range, then with small variation in wind speed, the power change can be relatively high. And then as it reaches its rated wind speed for which it is designed, then power that generator is producing is limited. And so here you have a constant range of power production. And then as wind speed gets too high, then it's basically the wind turbines, they pitch their blades to let this wind through and not, overload the generator. And so this power is kind of gradually decreased back to zero to protect wind turbines. So you can see here that, in this range, wind speed change doesn't do anything, but in this two ranges, there can be rapid variations with small variations in wind. Solar generation output can also instantaneously fluctuate due to cloud cover. So weather can change very rapidly. If you have geographic diversity between where this wind and solar resources go, it can help to smooth variability, because then you don't have really large wind and solar plants in one area and they don't get affected all at the same time with the same weather pattern. One thing to note is that electricity demand also varies all the time, because we switch on and off equipment all the time. Industries have varying industrial processes that also change load all the time. And so if you have combined what is called net load variability, this may pose the highest challenge. And what I mean by net load is think about load profile that you have throughout the day with industry and people consuming various amounts of power during the day. And if from that you subtract instantaneous solar production and wind production, then remaining load has to be served by other type of generation, say conventional thermal or hydro generation. And so if variability of load is kind of in the opposite direction, so load is increasing and at the same time wind production and solar production is declining, then these are the times when you get highest net load ramps. And so these net load ramps have to be served by a remaining generation, which should be flexible enough to be able to do it. And so what you can see on the right-hand side, some of you might have heard is a famous duck curve, because it looks like a duck. And it's showing hours of the day on x-axis and megawatts of net load on y-axis. So they basically already subtracted wind and solar production from load, and what you can see here is the remainder. And you can see that in 2013, there were relatively small variations in the net load, and this is this blue line here. But as they were adding more and more, this California, so it's basically more and more solar, then you get really low net load in the middle of the day when it's sunny, and even load is high, you still have a relatively low net load because all of this load is served by solar generation. But then in the morning when load is ramping up and solar is still coming up, they have this net load ramp down, which is a problem, but not as much, and they have potential over generation where they have too much generation more than they have load. But what is a bigger problem is increased ramp in the evening is when solar is already going out and load is still relatively high. And so there is this high net load ramp up, which is more than 10 gigawatts. And just to bring it into perspective, I mentioned in the beginning that 2 nuclear units that Texas has are about 4,000 megawatts. So it's almost like 3 times the size of nuclear units in Texas that you can get a ramp of within maybe 3 hours. And nuclear units are not flexible, so you need other gas-fired units are the most flexible ones. So you need those to be able to very quickly start up or will be ready there to ramp up their power production to address this ramp, because this ramp still needs to be served by somebody because electricity demand is not going anywhere. Yeah, so this kind of like a challenge I talked about, and some of the solutions that are being used is introduction of various reserve products. So some of the areas they went and introduced so-called flexibility products or ramping products. It's also possible to address if you have more frequent generation dispatch. So you don't dispatch your thermal generation every hour, but maybe you do it every 5 minutes and you can prepare for these changes in net load. You can also have more sophisticated dispatch of remaining generation fleet using multi-interval dispatch. So you kind of you look ahead. You don't just dispatch for 1 hour or for 5 minutes, but you look ahead for periods to come and how generation and load may change in the coming intervals. And so by doing that, you can line up flexible generation to serve that ramp that is about to come. So you don't get surprised by it, but more you position the system where it can serve that ramp. You can also do it by optimal sizing and placement of storage. So again, in the planning realm, if you already foresee that there will be a need for more flexibility, then having needed amount of storage may help, because storage is very fast, very flexible. But then another issue with that, you need to have sufficient amount of charge. So you would need to make sure that storage is charging during low net load hours to be available during net load ramp. This requires more sophisticated generation resource planning that takes flexibility into account. So previously, longer term resource planning was relatively coarse because generation was flexible and was easy to dispatch it the way you need. And so doing planning exercise, you might have had time resolution of 1 hour or maybe even coarser. But now, as we need this flexibility to address net load ramps, there is a need to have finer timestamps in the planning realm and consider needs for flexibility, consider various scenarios, looking at forecasts in the planning that may happen, and consider forecast uncertainty as well. Now switching gears to uncertainty challenge, wind speed forecast is uncertain already, but then wind generation forecast is using wind forecast and direction, so direction for wind, but it also requires information about wind plant layout, wind turbines, power curve, so that this curve that I was talking about previously. You need to know number of turbines that you have in a plant, and also a number of turbines that are actually available to produce power at any given time, to be able to accurately predict what an output of a wind farm will be. So again, similarly to solar, also irradiance forecast is uncertain, but then solar power production forecast is using irradiance, but also requires information about solar panels, plant size, plant layout, tracking mechanism that is being used. And so by tracking, I mean, in some solar power plants, the panels are fixed at a given angle, and in others, more recent technology allows you to rotate or like track sun with the panel, and it allows higher efficiency. So the solutions for this forecasting uncertainty is as accurate as possible forecasting with high aerial and temporal resolution. Forecasts need to be updated with high periodicity. Reserves can be dynamically dimensioned. So what I mean by that is previously system operators would procure reserves of fixed amount across the entire year, or maybe it would vary by season, maybe sometimes time of the day, but it's the same amount over the entire season. But now, as you see more variability and more uncertainty, it makes sense to dimension reserves more dynamically, kind of looking in the day ahead and saying, oh, I need more reserve today because my forecast is more uncertain, and I expect more variability during the day. You can do more sophisticated generating unit commitment and dispatch that takes forecast uncertainty into account. So you don't deterministically commit your generation, and by commit I mean like turn online your generation and dispatch your generation, but you do it more stochastically, considering that you will get forecast uncertainty. And then you can do planning with consideration of forecast uncertainty. So again, in the planning studies, you already include the fact that going into each of the days that you are, that you are modeling in your planning, you will have this uncertainty of the forecast, and it's not all deterministic. And if you do that, that planning exercise will result in more flexible reserves that are, ready to, or more flexible resources being built that can address this uncertainty and variability. So I brought this example of how this being, how this all being put together in ERCOT, and just shows the way forecasting is done for ERCOT. So so this is kind of with an example of hourly forecasting. So every hour in the beginning of the hour, each wind plant in ERCOT, and ERCOT has, I don't remember a number of wind plants, but it has 35 gigawatts of wind generation. So it's several hundreds of wind plants, you can imagine. They send site information, which is, status of the site, any D rates, meaning any turbines that are on outage, any cables that are on outage, telemetered meteorological data, and they send all of that data to ERCOT. ERCOT in turn sends it all to a forecaster, third-party forecasting company that is doing forecasting for the entire wind fleet in ERCOT. And they have information about layout of the sites, the power curves, and all of that technical information that they need to know to do power forecasting. So then they compute and send to ERCOT a rolling 168 hours generation forecast for all wind plants. So it's by plant, it's not system-wide. And so from that, ERCOT knows how much each of the plants is expected to be producing in the next 168 hours. And then ERCOT is using this forecast to make operational decisions, including unit commitment and dispatch. This forecast is also being used in market dispatch mechanisms and so on. And it is updated every hour. So it's a rolling window of 168 hours, and all of this process is being repeated every hour. And then additionally to that, ERCOT now has similar forecasting for solar. ERCOT also uses 2 vendors for wind and 2 vendors for solar, and that allows them, when they get forecasts that kind of looking strange, allows to choose between vendors, and they also always pitch vendors of how accurate forecast has been, you know, in the backcast, and that provides them kind of more confidence about which forecast to use when they see some unusual outcomes. And ERCOT also has now short-term forecast that has time resolution of 5 minutes and is updated every 5. It is updated every 5 minutes. Has forecasting horizon of 1 hour. Sorry, and this is used in real-time market dispatch. So I wanted to bring up this picture. So this kind of summarizes different options that we use now to address variability and uncertainty. I already mentioned that you can address it through introducing new reserve products, or you can address it by changing market design or market scheduling mechanisms. And so if you look at different types of variability first, so if you have a variability between intervals, so that's kind of longer term variability between different scheduling intervals. So as I mentioned, in the market framework, multi-period scheduling with look ahead can help, because if you can look ahead and see that you have this variability coming, you can position your remaining generation to address this variability and uncertainty. Or you can do it with flexible ramping reserve. So you reserve certain amount of capacity to address this variability, and you can address it that way. If you have variability within interval, then by having shorter scheduling intervals, you can reduce that variability, because if you redispatch your remaining generation more often, then you can address variability just through market dispatch. But on the other hand, you can also have frequency control, or it's called regulation here in the US, reserves. And so these reserves specifically meant to address the short-term variability within scheduling intervals. Now going to uncertainty, if you have uncertainty between different intervals, you can have increased scheduling frequency, or you can also have stochastic or robust scheduling, where you kind of look ahead and at different uncertainty, different scenarios for forecasts that you have, and you can position the system in the most optimal way to address this uncertainty. Or you can have flexible ramping reserve and do it kind of more deterministically. You determine how much reserve you need, and then this reserve is available to serve this uncertainty. If you have uncertainty within interval, again, shorter scheduling intervals help, or doing some kind of stochastic dispatch decisions also helps. Again, you can address it with some kind of reserve products. And then if you have uncertainty that you already predict before the first interval, then having closer to the shorter gate closures helps. And again, having stochastic dispatch helps as well. And by shorter gate closures, I mean, say, for example, ERCOT runs economic dispatch in real time every 5 minutes, and it's at the top of 5-minute interval. And to run the dispatch for the entire ERCOT system takes about 20 seconds. And so by the time the decision is made, you don't see much of the change happening on the system for, system conditions. So you're pretty well set with these dispatch decisions. But in some other areas, for example, in California, at least a while ago, I'm not sure if they changed that, they were running real-time dispatch 15 minutes ahead of that time when they use this dispatch. And so 15 minutes is relatively long time. And during this time, wind can change, solar can change, load can change. So by the time you arrive to this operating interval and you send this dispatch instructions to generators, you're already facing a large error. So having this gate closure closer to the time when you'll use the decision is better. All right, so now a switch to technology challenge. I mentioned that wind and solar and storage, they're using different technology, and that introduces a set of challenges associated with that. So conventional fossil fueled and hydro generators, they're using large synchronous machines. So these are big rotating machines, but these are all kind of concentrated in one area, and a blueprint is less than for large wind or solar farms. When connected to the grids, the synchronous machines are rotating in synchronism. Each generator speed is proportional to so-called synchronous speed, which translates to electric frequency. So, in the GB, it's 50 hertz system. In the US, it's 30 hertz system. So I just translated, and the 50 hertz system translates to 3,000 revolutions per minute synchronous speed. So not all of these generators rotate with that same speed, but the speed of rotation is proportional to this 3,000 RPM. And the name synchronous machines comes from the fact that they all rotate with the speed that is either synchronous speed or proportional to synchronous speed. So what it does is when one generator on the grid disconnects because of, say, some malfunction, there is kinetic energy stored in rotating masses of these synchronous machines. So these are large rotors, and they have kinetic energy. So this energy is being used to replace lost generation in the first moments after it happens. And this is also called inertial response. This allows to keep balance between production and consumption. So production and consumption should always be in balance. You lost one generator, but your electricity demand didn't change because of this loss. And so it needs to be supplied by something. And so in the first moment after generator trips, this power consumption is being supplied through kinetic energy stored in rotating masses of all the synchronous machines. But as a result, because these generators give out the kinetic energy, they slow down, and electric frequency in the grid falls as a result. So it becomes something less than 50 hertz. And then there are additional controls that they are using this electric frequency as a signal, and they add power to the grid to bring frequency back to normal. So basically they sense that frequency in the grid is falling, and they say, oh, I need to produce more power. And then they use more prime fuel, say, for example, gas or hydro, will be water, and they inject more fuel into the turbine and produce more power if they have headroom to increase power production. And with that power, the lost generator is replaced, and this stored kinetic energy can be kind of recovered, and frequency can go back to 50 hertz. So it then all goes back to normal. So this inertial response, so this type of response is kind of like a wide area communication. But the beauty of it is it's also inherent and instantaneous and synchronous machine. So it's all happening without any external communication, but also without any local measurement of anything. It just, by the virtue of all of these generators being connected and being synchronized with each other, after a loss of generation, this replacement in the first moments with kinetic energy stored in rotating masses of synchronous machines is happening automatically without any control action. And so this allows to keep production and consumption always in balance. But wind, solar, and storage resources, they don't use synchronous machines. They are connected to the grid through power electronic inverters that convert power that is being produced at the source to the signal that is, synchronized with the grid, with grid frequency and magnitude that is needed. So basically what it does is that this inherent and instantaneous response is lost. So you can see this converter is kind of like a wall that doesn't let wind, solar, and storage generation to see what is happening on the grid without any external measurements. And so they don't react in the same way as synchronous generators do. Currently, this wind, solar, and storage generators, they rely on local controls to measure electric frequency and then respond. And even though their response is very fast and actually faster than that of control activated response of synchronous machines, it's still not instantaneous. So when I was talking about here that, on synchronous generators, there are additional controls that they will sense frequency decline and they will inject more power into the grid. These controls are slower in synchronous generators compared to inverter-based resources such as wind, solar, and storage. But this instantaneous kinetic energy injection is not there because there is this kind of inverter wall between the grid and the generators. So this introduces a challenge of keeping balance between production and consumption and keeping frequency within 50 hertz within narrow range. And so what is done today is, as I mentioned, in Ireland, for example, they are keeping certain amounts of synchronous generators online. So even though wind and solar production may be very high and high enough to serve the entire load, they need to keep certain amount of this big synchronous machines online to provide this reliability service, if you will. And if they turn them off, then there is no way to keep balance between production and consumption all the time. Additionally, what can be done, faster reserves can be used. So with that, it allows you to have less of this kinetic energy stored in the system. You can have less synchronous generators online. And if you have faster frequency response, so you address these changes in frequency very quickly, and with that you need less of synchronous generators online, but you still need some amount. It allows you to have less reserves and kind of costs less, but again, doesn't solve your problem completely. And then there is a new technology of inverter, new way of inverter controls. And Janusz, I think you mentioned somebody already talked about grid forming controls that allows inverter-based resources to act a little bit more like synchronous generators and provide services nearly instantaneously and inherently, and with that support system, with support system reliability, and with proliferation of this grid forming inverter-based resources, you can theoretically go to 100% wind solar storage on the grid instantaneously. So some of the islands, as you've seen on my first slide, already going to 100% penetration, and that is possible because they have some of the grid forming inverters on the grid. Another challenge is, so that slide was about keeping frequency. This challenge is about keeping voltage. So to sustain reliable operation of both loads and generators, voltage also needs to be maintained within a narrow range across the entire system during a normal operation, and it also needs to recover back to normal as fast as possible after any disturbances that may happen on the grid. And so when short circuit faults are happening on the grid, you can imagine, like, I don't know, tree falling over a transmission line, and there is a short circuit fault on the line. Sorry, what?
No, go ahead. Sorry, I was coughing.
Sorry. Yeah, so when you have a short circuit on the grid, the way synchronous generators behave, this large conventional generators, they are designed to keep voltage at the terminals constant, and that results in instantaneous and inherent increase in current. So you'll see very high fault current flowing towards the short circuit location. While this, large current is bad in some regards because it's high and it may overload the lines and, burn up the conductors, this property also allows fault detection and isolation of faulty element by protection device, because this protective device that sees higher current flowing on the line, it's unusual, and it says, oh, it's a short circuit, I need to isolate it, and does that very quickly. And then voltage recovers on the grid fast because synchronous generators, support voltage. But wind solar storage resources today, they behave differently during fault. They maintain constant current during faults because they were just designed this way initially. Therefore, there is no inherent change, and it may be hard to detect clear fault by protective devices. So if you have area with high concentration of just wind, solar, and storage, and you don't have any synchronous generators in this area, a fault happening on the line, and there is no visible increase in current flowing on those lines. And so protective devices cannot say, well, there's a fault happening, I need to clear. So that's a problem. But also another thing is that these modern day inverters, they are equipped with controls that have a short delay, and they can provide voltage support and aid system recovery. But these controls, they rely on measurements, and so they have time delay. So it takes time before inverter-based resource such as wind, solar, or storage starts supporting the grid during faults, whereas synchronous generators, again, similarly to inertia, are doing it inherently and by design. So again, in grid forming converters, controls can be done differently, and so it makes an inverter act more like a voltage source. So it keeps voltage at the terminals constant, and when a short circuit is happening on the line, this results in instantaneous injection of higher current. It's still, though, within the rating of the inverter cannot overload, so synchronous generator can produce currents up to 5 times its rating during faults. Power electronic equipment is very sensitive, and it can only go up to its rating, maybe a little bit, maybe 20% higher. So again, this issue of detecting faults still stays, and it's a kind of a research problem to solve, how to use different protection techniques. There are different protection techniques, but also how to do it economically without replacing the entire protection systems that we have today. So this voltage control issue is resulting in something that is called weak grid issue, or sometimes you can hear system strengths term. So what it means is that in areas with high concentration of inverter-based resources, that being wind, solar, storage, that are far away from synchronous generators, you have this weak grid, and as I mentioned, fault clearing may be challenging, but also there can be issues with control instability that may result from generator controls being too fast and fighting each other. So what happens if you have a large concentration of inverter-based resources far away from strong voltage source, that being synchronous conventional generators, any injection of current in that part of the grid results in really high jumps in voltage. And so you're trying to control voltage from inverter-based resources, and you're trying to help the system, but any current that you inject results in really high voltage. And then you say, oh, voltage is too high, I need to respond and inject less current. So you start injecting less, voltage falls very quickly, very low, and it results in these oscillations you can see on the right-hand side. That's from actual plant in West Texas. And this actually with without any disturbance even happening, this is just power is from the plant is fluctuating, and because it's very weak grid and there is no strong voltage source, voltage is very sensitive to any change in current injection into the grid.
What was the frequency of oscillations over there? Can you tell us something?
I think it was around 10 or 12 hertz, if I remember correctly.
Thank you.
Yeah. Yeah, and so you can see this part of the grid here circled, and I showed this in the beginning. This is Texas Panhandle, where there is very few synchronous generators, a lot of wind. Now more solar is being added, then later on in the nearby area, there is also increased development of inverter-based resources, and all the large generators are here in the central and eastern part of the grid, large synchronous generators.
Sorry, Frank, I can see wants to ask the question. Frank?
Yes, so I had a question. So earlier on, you mentioned that the response of the inverter-based loads was fast but not instantaneous. Do you know what approximately the delay is in the response? Is it 50 seconds or?
So for frequency response, it's about 250 milliseconds.
Okay.
Yeah, for current injection, there are different requirements. If I remember correctly, in GB, the requirement is within 20 milliseconds, if I remember correctly.
Okay, great. Thank you.
Sure. Yeah, so just to summarize, why is it a problem? We have a grid of today, so maybe this is not of today, this may be of yesterday, where you had this large amount of synchronous generators on the grid, and maybe just a few inverters marked with this green circles here. But we are heading of the grid of already today and tomorrow, where synchronous generators will be just a few, and the grid will be dominated by inverter-based resources. And some of these inverter-based resources are even on the distribution grid, so there is less visibility and less controllability from the system operator, transmission system operator point of view to these resources. And so the challenges, as I mentioned, is more complex equipment. There is uncertainty about its performance, differences in implementation of required capabilities. This results in complex modeling. There are faster dynamics that previously were not looked at in the simulation tools. So there is a need for more detailed tools that will capture all of this fast dynamics. The solutions are standardization of interconnection requirements. I think Europe is much more ahead of the US in that regard, with having more harmonized interconnection requirements for generators, but still those requirements somewhat vary on national levels. We need further development of inverter control capabilities, improvement in modeling and simulation tools, supporting supplemental equipment. So there are ways to have kind of transmission level equipment that provides support, and it's not necessarily that it's a synchronous generator, but there are other pieces of equipment that can provide support as well. And also unlocking additional capabilities with inverter controls. So as I mentioned, which is broadly termed as grid forming. So this figure is just a schematic. It's not a physical representation, but it's basically on x-axis is showing instantaneous penetration of inverter-based resources, wind, solar, storage. And by instantaneous penetration, if you remember from the first slide, it means a percentage of load that at any instance is served by inverter-based resources. And on the secondary x-axis, you can see an indication of system strengths. And so on the left-hand side, you have the strongest grid, where you have a lot of synchronous generators supporting the grid. And on the right side of the spectrum, you see weak grid, extremely weak grid, where you don't have any big synchronous machines supporting your grid, and everything depends on inverter-based resources. And then here, just schematically, you have this line in the middle that shows the limit between stable and unstable condition. And so everything above this line is stable, everything below is unstable. And so it kind of grades the system into this conditions of percentage of penetration level and system strength. So before, we had this really strong grid with very low penetration of inverter-based resources. And initially, that maybe some 10, 15 years ago, inverter-based resources were allowed to do whatever. So as soon as the main purpose was to inject megawatts in the grid, and as long as something happens on the grid, some kind of disturbance, they were actually required to get out and not interfere with what is happening on the grid. Then gradually, as we started getting into more and more inverter-based resources, that was not allowed anymore, and they had to support the grid with some kind of grid-friendly features. And one of the first ones was ride-through capability. So if disturbance is happening on the grid, a generator inverter-based resource has to stay connected and support the grid recovery. And so as we started getting into maybe like around 50%, then inverters in those weak grid areas were required to have specific controls, which are called weak grid features. So controls are specifically designed to avoid this control interactions that I mentioned, but also grid enhancing technologies such as dynamic line rating and use of flexible power electronic supporting devices on the grid is also more broadly used now to support the grid, because now you have less synchronous generators and more inverter-based resources, and so something needs to support this reliability of the system. And then if you move further now, getting into really high percentages, maybe 70%, so where Ireland is today, where ERCOT is today, you need 5 further control advances from inverter-based resources. So as an example, today in ERCOT, there is a fast frequency response service implemented where batteries can participate, providing this really fast response. And as I mentioned to Frank's question, it's within 250 milliseconds. You need to provide active power injection, which is very fast compared to frequency control from synchronous generators, which takes about, it isn't nearly instantaneous, but takes about 10 to 12 seconds to ramp up to full power. Then synchronous condensers are being used more broadly. So these are synchronous generators without a prime mover, and this rotating machine is just being used to support grid voltage and frequency. And so these devices are being placed across the grid to provide some stabilization services in the absence of synchronous generators. And then as we get into above 70%, maybe to 100%, then we definitely need grid forming control. So we basically need inverters to take charge and act more like synchronous generators act today, supporting voltage, supporting frequency, and providing all of the essential reliability services to the grid. I wanted to just briefly mention the performance and modeling challenge. I think it may be more of an issue in the US, although I'm not sure if the reason why we don't see it in Europe is because there is kind of, the European system is highly interconnected and there is maybe less systematic approach to analyzing these disturbances. But basically what's happening in the recent years in the US, not every time, but at times when disturbances happen on the grid, maybe like short circuit disturbance, we see a simultaneous disconnection of high amounts of inverter-based resources. So instead of just one generator tripping offline, you can see, I don't know, 20 generators tripping. And you can see here on the right-hand side, a chart of all different events. Yellow is solar generation that got tripped, blue is wind, and gray is other, which is primarily synchronous generation. Orange is distributed solar resources. And you can see that as you have a fault happening on the grid, it's already stressful enough event, but at the same time you lose, so the largest, most recent event in Texas was more than 2 gigawatts of generation at the same time. And it's pretty stressful for a system of ERCOT size and very concerning. And this is not just one plant, this is across many plants concentrated in one area where this fault has happened. And as I mentioned, currently inverter-based resources are required to stay connected during faults, but they still do disconnect. And so the problem then in the event analysis is to understand why is this happening. So they are not behaving according to requirement. Why was not this detected during interconnection studies when system operator investigated this generator during interconnection process? Why was this not seen? And so what it turns out is that, first of all, implementations of controls are very different. And sometimes the manufacturer intends one function and then it harms some other performance. Some of the functionalities are not represented in the models. And this was because it was not considered important previously. So for example, some of the protective functions even in inverter-based resources are not included in the models because in the philosophy of manufacturer, this protective functions is to protect equipment and do not have anything to do with the grid. But in reality, when the fault is happening and this protective equipment disconnects the plant, it becomes a problem. And then also what was noticed, and probably like in the interest of time, don't go too much into details here, but what was noticed that in the simulation domain that we're using today, with the time step that we're using today and level of details that we are looking into, some of these behaviors are not even captured because these behaviors are happening on such a fast time frame that are not included in the models, and we, even if they were included in the models, we wouldn't be able to see anything happening there. So that indicates a need for more detailed studies than what we've done before. And these more detailed studies, they are computationally very intensive. And currently, so in Australia, for example, they have currently a model in what is called electromagnetic transient domain. So it's a detailed study, represents all three phases of power system and simulates with 10 to 50 microseconds time step. So it takes really long time to do a simulation of a single contingency. So you say you have a fault on the system or you lose one line and you want to simulate what happens in a time frame of maybe several tenths of a second, or you know, maybe a second or 10 seconds. It takes 2.5 hours to simulate. So it's really a long time. And it's impractical to do it. So and so in Australia, they're really working on increasing this computational efficiency and doing the studies faster. In other areas, engineers are only focusing on certain areas of concern, such as like weak grid areas, what I mentioned. So this is something that they do in Texas. They only simulate this Texas Panhandle in this more detailed study where every generator or a group of generators that are closely connected are modeled separately and simulated on a separate core. And then, you know, there is a master case running, and all these different slave cases, they kind of talk to a master case that has a network representation, and the rest of the ERCOT grid is represented as an equivalent. But even for this ERCOT system, part of the system, what's happening with more and more inverter-based resources, this case is becoming bigger and bigger. And still, again, it's just 500 buses. That's compared to 5,000 plus nodes that ERCOT grid has on the system altogether. There are 60 models of inverter-based resources representing just 10 gigawatts out of 35 gigawatts of wind that we have. And it takes 2.5 hours to simulate one fault on the grid, which is, you know, usually we simulate thousands of contingencies for one planning study. So this is a good way to dig into a problem, but this is not practicable for planning studies, and let alone studies that you need to carry in operations closer to real time. So really, like, a lot of help is needed here to increase computational efficiencies, because these more detailed studies are not going anywhere, and we will have to continue doing this moving forward. And so just one last thing I wanted to mention, just to make it even more complex. So we are getting into this paradigm where we have more detailed dynamic studies. We're having to do more detailed dynamic studies that take long time. I talked about need for more detailed resource planning studies, transmission planning studies, with all of the different constraints being represented, going to lower to higher resolution. So basically having smaller time steps in the planning studies. But what also is important now, we are relying more on remaining gas generation. And so that requires maybe natural gas system modeling. So you might have heard what happened in Texas in February 2021, where a lot of generation got lost, and a lot of that generation lost was gas-fired generation And the reason was that the gas supply was not sufficient to those generators and they couldn't produce power. And so currently ERCOT has no visibility into gas supply system and what may happen with it during these extreme events. Whereas ideally you would need to co-optimize, what is happening in the natural gas system and what is happening in the electric system. And then, as I mentioned, more and more of this inverter-based resources is also going on the distribution side. And then now system operator on the transmission side need to have some visibility into what's happening there and include distribution system modeling in its planning studies. So this makes the problem, very complex. There are no tools that combine all of this together today. And so basically we're left with tying tools that we currently have, but even passing data from and modeling models from one tool to another is relatively difficult. So this is another kind of challenge that we're facing today. And with that, this is all I had, kind of a whirlwind of challenges we have with wind, solar, and storage resources and why they were not there before.
Well, thank you very much, Julia. Excellent presentation, giving overview of all the kind of problems. So I think, first of all, how much time do you have for discussion?
I have about 20 minutes. I have to hard start at 9:30 my
all
time.
Right. So may I just abuse my chair powers and ask a question, because we've had discussion about oscillations, about the 8 Hz oscillations in this country. And I've been, I contacted people at ERCOT and they're saying there are some 5 to 15 Hz oscillations due to those inverter-based resources on the system. Do you know something about that? How they can, is it a big problem? Was it replicated EMT studies? Do you know something about it?
Yeah, so that's what's happening. It's probably this one is the best. This was first time they discovered it in 2012. That's first time they saw this. And this basically because of weak grid issue, this what you can see on the right hand side here is a plant connected, weakly connected to the rest of the grid, far away from synchronous generation. It was connected with 2 transmission lines, but one was on outage at the time. And so if you have 2 parallel lines, then electrical distance to the rest of the grid is kind of twice less. Whereas if you have just one line, with one line being on maintenance, it kind of doubles the electrical distance to the stronger sources. And it makes the grid for that generator, even weaker than it was. And so as power started increasing at that plant, they saw this voltage oscillations without any disturbance on the grid. This was just from extra injection into the point of interconnection from a resource. So they saw this first time. They were able to replicate it in studies. And then there are also other, so these issues are being studied for during interconnection, and also every quarter ERCOT runs what they call quarterly stability assessment. So they've split the grid into a number of areas, and they look at all new generators that are coming online within a given time frame. And basically they have all existing generators modeled in the case. And all these new inverter-based resources that are coming up also modeled in the case with detailed model that were provided by inverter-based resource manufacturers. And in this case, they are looking for any kind of instabilities, oscillations, weak grid problems. And if they see that, what they can go for is control tuning at a given resource, or transmission reinforcement if it makes economic sense, or ultimately that results in what they call stability constraint. So what it means is, see here, there is this line, maybe around Panhandle, there is this circle, right? And it crosses all these lines that are going out of Panhandle. And so they say, well, if I transfer more than given amount from these lines, it means that, this megawatt amount is being produced here. There's very little consumption, so all of it is flowing out. And if I have this many megawatts produced here, I see these problems. And so in real time, they're saying, oh, because of the stability considerations, I cannot transfer more than X megawatt from here today. And this is being calculated in the day ahead based on system configuration at the time and based on wind and solar forecast at the time. So they basically look at what production is expected in the area, what is system configuration, what are studies saying can be stably produced in this area. And if the amount that is available is more than what can stably be produced, then all of that generation is curtailed. So that's the most common mitigation today, unfortunately. It varies. I mean, the good thing is that it's not constrained all the time to just 1 megawatt amount. They reevaluate based on system configuration at any given time. So that allows some flexibility. They have installed 2 synchronous condensers in the area. So as I mentioned, synchronous condenser is like a synchronous generator without prime mover, and it provides same system strengths advantages as a synchronous generator does. So they installed 2 of those in Panhandle area to address weak grid issues, and that allows to increase megawatt amount that is produced from inverter-based resources here. Another issue is some of this longer transmission lines going to central part and East Texas, they are series compensated. So as I mentioned, these are special devices that are placed on the lines to effectively decrease electric distance to strong voltage sources. And so all of these lines are series compensated because all of them are long, and to allow higher transmission, they had to do that. But what happens is that if in a number of contingencies, an inverter-based resource plant, and specifically wind plants, get radial with a line that is series compensated, then there can be oscillations between the series compensation device and inverter-based resource. And so this is also a known issue. It happened in operations first time. That's when ERCOT learned about it. It's when during a fault happened, fault got cleared, and it left a wind plant radially connected to a line that was series compensated. And they saw these oscillations in real time. The plant got damaged. And then after that, ERCOT started looking into this subsynchronous oscillation problem. And so now every plant that is going through interconnection process is being screened for this issue. And so if it can become radial within 4 or 6 contingencies, I don't remember correctly, it can become radially connected to series compensated line. Then they need to do a detailed EMT study and look for mitigation in case of subsynchronous oscillations.
Do you know what's the frequency of those oscillations, subsynchronous oscillations, due to series compensated lines?
I think that's also around 8 to 10 hertz, if I remember right.
Yeah, okay, thank you very much.
Yeah, and another thing, the lower frequency oscillations around maybe 0.2, 0.5 hertz. They've also noticed in the studies with this 2 synchronous condensers in Panhandle are the only synchronous generators in this area. And then the nearest synchronous generators are very far away. So they noticed that during some contingencies and some system conditions, they can see inter-area oscillations between synchronous generators, on one side of long transmission line and on the other side of long transmission line. So those oscillations are like 0.2, 0.5 hertz.
Sorry. Yeah, so Frank first and then Chris.
Thanks, Julia. That's a really, really interesting presentation. So I just was struck by your comment about the time delays for the fast but not instantaneous response. So, I mean, so Yanis, I'll look to here to tell me if I've got this calculation right, but the sort of simplest control loop with a lag, just a sort of linear feedback would if it had a 35 millisecond delay, then I think I'm right in saying that would produce as it went unstable, that would produce if the gain is too high with a 35 millisecond delay, then as it goes unstable, it'll produce a periodicity it'll produce an oscillation, but with a period of 4 times that. That's 140 milliseconds, which is, I suppose, about 7 hertz. So, I mean, just looking for the simplest possible explanation to rule that out before looking for something more complicated, one would look for whether, you know, just delays in the response was itself just what was producing it. Yeah, I mean, you emphasize the point that these large spinning masses have the huge advantage that they produce a wide area communication at the speed of light, and with no software delays, no delays other than the speed of light delays, which are trivially small in the systems that we're looking at compared with, you know, anything we look at in terms of 10 milliseconds or whatever. So I just wondered about that.
Yeah, and you're completely right. So remember, I mentioned this weak grid controls, and that's exactly it. So basically, they are looking at optimal way to slow down controls in weak grid areas where they're still effective for voltage recovery, but they don't result in these oscillations. So that's exactly what they do. They're slowing down controls in weak grid areas, but there is a limit to that because then they become too slow. And if you only have inverter-based resources to support voltage in that area, then if they are too slow, then recovery becomes slower.
You can see the conflict in people's minds because that is not as fast as the physical spinning mass. Might induce you to turn up the gain so that it becomes faster, but of course that destabilizes it with a delay. So so you're stuck. But Yanis, let me hand on to someone that knows what he's talking about here.
I mean, but you're exactly right. That's exactly is the problem, and the problem is you kind of like between two fires. You go too fast, then it's unstable. You go too slow, then it's ineffective.
Sorry, Chris, you want to ask a question?
Yeah, it's somewhat related to Frank's, but Frank proposed a possible answer to it. I was going to ask, out of the simulations in Texas and in Australia, whether we have any intuition as to what the physical origin of these modes of oscillation are. We have the well-known physical origin of inter-area oscillations between traditional synchronous generators, but I was wondering whether we have any equivalent here.
So I'm not sure, because say for example in GB it took I haven't read like the final report from that oscillation event, but last time I heard them talking about it, it was a few months after the event happened. They still couldn't find what the cause was. In ERCOT, like from my experience, they had these 3 causes of oscillation, so it's relatively easy. Maybe that's because how the grid is, that is, more, you have this isolated areas with inverter-based resources, nothing else there. So it's more kind of clear-cut case. And they can kind of isolate it to a group of inverter-based resources in a weak grid area in case of, voltage stability issue. It can be isolated towards the, say, plant connected radially with a series compensated line. And that inter-area oscillation between synchronous condenser and synchronous generators that they saw, that was only in a study, but was also kind of clear what's causing it. Yeah, so in ERCOT, they haven't basically experienced yet where it's kind of hard to say what's causing it.
Yes, it was when you say what's causing it. One thing we were wondering yesterday in the Australian case is that they can reproduce it in simulation.
Mm-hmm.
But does that mean that we have a sort of simple understanding of what the mechanism is that's leading to it, as well as with maybe as we say in the Texas case, which generators are implicated?
Yeah, I'm not sure. I think it's kind of case by case, I would say.
Okay, I have a question from Yanis. Please go ahead.
Yes, many thanks also from my side for the very nice presentation. So I wanted to ask if in Texas you are making use of grid forming control from inverters to provide support to the grid.
Yeah, I wish. I'm trying to kind of push for it and promote it as much as I can. It haven't been used yet, but what worries me is that they have about 7 gigawatt of batteries in the interconnection queue with already signed interconnection agreements. So these projects are relatively likely that they will materialize. And none of these projects is being currently, designed as grid forming because there is no incentive, no requirement from ERCOT side to have grid forming inverters on the system, and there is no market for some kind of product like what they have in GB that prompted some of the grid forming inverter development. So what I'm trying to do now is to motivate ERCOT. So we're already starting a study now with ESIG, the company I work for now, to look at benefits of grid forming inverters for ERCOT system. So we are hoping we can show benefit, especially in these weak grid areas, and to say that if these generators, these batteries that are currently in the interconnection queue and they are going in the weak grid area, if instead of being grid following, they are grid forming, that if we can show that there is a benefit in that, then maybe ERCOT will, the next step would be ERCOT will either somehow incentivize or have a requirement for grid forming capability. But currently no, and they're also looking at using synchronous condensers to support the grid more beyond what they have. So currently they have 2. They are looking for more. One thing that is kind of underlines the urgency of having maybe a computational burden resolved for EMT studies is that currently system operators are looking at synchronous condensers not only as a solution for technical issues, but also as a solution that allows them to continue using this more simple type of simulations that we're using today, like phasor domain simulations instead of EMT. So it's just like practical issue. Just for simulations, it makes sense to install certain certain hardware on the system rather than going for more advanced inverter controls. Because even with grid forming inverter controls, there still will be a need to do detailed EMT studies.
Okay. Thank you, Julia. So it's a tail wagging the dog, essentially, just simpler simulation.
Yes.
It means that they don't use more advanced controls. Any other question?
Yeah, but also, I mean, the disadvantage with synchronous condensers is that you need additional equipment, whereas what we're trying to show in the study is that if you equip batteries that are already going in as resource with grid forming controls, they can provide same support, but you don't need this extra kit. So yeah, there is economic benefit in that as well.
Well, but we've discussed it here, and I think one of the reasons is conservatism of system operators, because they're not incentivized to go bold where no one has gone before, but they're basically, the one thing they worry is about things go wrong. And when you have physical inertia, rotating, it will deliver what you ask it to deliver, while with those controls, things may go wrong.
Yes, yeah, and also, I mean, the same issue will apply to what I showed with disturbances that we're seeing on the grid today with grid following inverters. Same issue will be there with grid forming as well, is that there is no certainty in the models, and that all controls and all protections are been included in the model that matter are included in the model. So I think there'll be a learning curve where we'll see same kind of things happening where they behave unexpectedly. So that's something we need to learn.
Okay, and okay, please, Simon. Yeah.
Hi, Simon Tidmans here. Just a question, and I may have missed it on the simulation method slide. So maybe it's good to between the phasor and the EMT simulations. So maybe the next one. There's this kind of overview. The next one forward, I think. And after this, yeah, here you go. So, and this is something I just heard about and kind of vaguely read about, but not, know much about, but I'm curious for your opinion. So there's this kind of phaser simulations and EMT simulations, and there's also people working on these kind of various, dynamic phasers or other, representations of that. Is that something that's potentially a solution to some of these things? So more advanced, representations that are not quite EMT, but at least capture some more stuff than you can currently capture.
Yeah, there is a kind of advantage in that. Is if you look at this EPRI paper I linked up here, there'll be more details there as well, and it talks about even some of the models. Some of the things that currently not included in the phaser domain models. If they were not included because it was not considered that within this time frame it matters to model these things. But if you include some kind of approximation of this, like say PLL loss of synchronism, you can include in the phaser domain simulation, and you need to have higher time, like to a lower time step for the simulation, but you can still capture some of these dynamics, and at least you can use it for screening to tell you if you need EMT study or not. And definitely there is also a middle ground with dynamic phasers where you can capture at least some of these issues, and maybe it allows you to just screen and help not to go for EMT studies for certain cases. So what you can see here, I didn't talk more in details about it, but these are causes of tripping, and this is a table from EPRI paper, and it basically shows where it cannot be represented in the domain because of limitations of the domain, but where it says yes, it means it can be represented, but maybe it was not because it was considered not important in the past. And then an EMT domain, all of these causes can be represented, but again, they were not included in the models because it was not considered important. Okay, so there are two issues, most like from a modeling accuracy side, but also from simulation domain side, and there more can be squeezed out from the simulation domain today to capture some of these things.
Thanks. Yeah.
Thank you very much. Over half past 3 that you have.
All right.
Okay, so thank you very much, Julia, for excellent presentation. So once again, round of applause, please.